And today's been a day full of technical difficulties. I will have one that's entirely my fault. Okay, so those of you just joining the recording, opposed to the, you missed when I discussed this announcement, but here's the idea. Don't worry about getting things done on time to a point, and do a concept check for that section before a homework on that section. It's a reading quiz, so read the stuff. And you'll be fine. Okay. So you don't scramble to get two things in to do tonight. I'm not going to be looking for them. I do try to grade in a timely manner, depending on what I have going on. Sometimes that works better than others. But like, you know, there's never a situation where like, oh, here's the due date, I'm ready to grade. That's not going to happen. Usually like the following weekend, like I ruin a Saturday afternoon and grade your stuff. Okay. All right, so here we have the second part of section 2.1 on convergence. All right, so what we're going to see in both courses in the sequence, 460 and 461, certain algorithms are iterative. Like for example, toward the end of the semester, we're going to see methods for finding the solution of equation f of x equals 0, so finding a root of a function. And so these methods, such as Newton's method, will generate a sequence of approximations that, if the number of iterations n is allowed to go to infinity, it would converge to the exact solution, but of course we have to stop sometime. Now, in more pure math classes, there's a lot of interest in convergence, like in real analysis, for example. Interest in, does a sequence converge or a series converge? But often it stops there. Like, either it converges or it doesn't. In some cases, can the limit be found? Like, for example, computing the sum of a geometric series, in which case that's possible. But in numerical analysis, there's a different focus. Not just on whether it converges, but how rapidly does it converge? Why? Because we want a sequence to converge to the exact solution as rapidly as possible. And we're going to have to stop the number of iterations sometime. And when we do, we'd like that error, the difference between the latest iterate, like the an, and the exact value, to be as small as possible. That's what we're going to look at here. Rate of convergence of a sequence to a limit, when it's already known to converge. So here's some notation to help us discuss convergence. Big O notation. So we have two sequences. So you can think of the sequence as a function of the index n. So basically, it's a formal definition of a sequence. It's a bijection, in which the domain is the natural numbers. So this sequence is big O of this sequence if it's possible for n sufficiently large to bound the first sequence by a constant times a second. So can you say, as n goes to infinity, that the two sequences are directly proportional to one another? Now, in some cases, you can actually find the constant c explicitly. And here's an example of that. So here's a sequence that I just made up. So we have a polynomial in n. And I would like to find a simpler sequence, Bn, that can be used to bound the terms of this one. So what I can do is, if I want to find a simpler upper bound for this, I'm allowed to perform any manipulation that makes this larger, because I'm looking for an upper bound. So, for instance, I can replace 3 and 2n by 3n squared and 2n squared, because n is a natural number, greater or equal to 1. So in that case, I have this upper bound, which allows me to combine these terms, and I can say that terms of sequence are less than or equal to 10n squared. So I can say that this sequence is order n squared. So in this case, a constant c is equal to 10. Now, generally, we don't really care what the constant is, but really, what is the sequence that goes in here? The simpler sequence that describes, in this case, is the rate of growth. This sequence is not converging to anything, it's growing. It goes to infinity as n goes to infinity. But we're going to be interested in sequences that converge to a value as n goes to infinity. But this is just to illustrate how you can perform algebraic manipulations to find upper bound of a simple form. And I'll do the same kind of manipulations for the case of a sequence that's converging to a value as n goes to infinity. So here's how we define rate of convergence. If we have a sequence, an, that's known to converge, so we figure out the limit first. Then we look at the difference. So basically, you think this is an error in an. And we want to have an upper bound for that. So we can find a sequence that satisfies this, really is an inequality, then this sequence Bn is the rate of convergence. So here's an example right here of a sequence an. So this sequence, it converges to as n goes to infinity. And you can figure out that out in different ways. For example, you can use L'Hopital's rule. Or you can use, you can divide top and bottom by n squared and simplify and conclude that it goes to that way. So what I'm going to do now is look at this minus 2. So that's what I've done here. This is just, I'm subtracting 2, but I want everything over a common denominator. Actually, I make that clearer. I'm going to put that in here explicitly. Okay. So the difference between that and 2 is given by this. So then we simplify as much as we can. And this is what we get. Now remember, to get us the simplest upper bound possible, I can perform any algebraic manipulation that makes the whole expression larger. For example, if I make the denominator smaller, it makes the fraction larger. So I can say that this is less than or equal to 2 over n squared. So in other words, the rate of convergence is n to the big O of n to the minus 2. So in other words, as n increases, the difference between an and the limit 2 is proportional to 1 over n squared. So that's fairly rapid convergence. It'll be much faster than, for instance, if the rate of convergence turned out to be order 1 over n. Now, if you're not able to get a bound as simple as this, like maybe you have multiple terms, the power that is closest to 0, that's terms of rate of convergence. So for example, if I had big O of, say, n to the minus 2 plus n to the minus 3, well, n to the minus 2 is larger than n to the minus 3. It's going to 0 more slowly. So the term of the power is close to 0, that becomes dominant. So that's how we determine rate of convergence, if there's more than one term in this expression. So questions about this example?
Professor, I think the sequence an is also a rate of, or maybe big O of a cubed. Yes.
But
we do not say that AN, the sequence is has the rate of convergence of n cube. N cube 1 over n cube, right?
Wait, oh, okay.
So I think it is concerned about another big theta notation. Because, yes, it is not said that it is the best bound of.
Okay, so you're talking about the non-uniqueness
Yes.
of it. Okay.
Because we can choose n cube or n4 square, yes.
The problem is, okay, you can choose, yeah, so this is the sharpest
Yes.
rate that's shown here.
Exactly.
But if you're going to go something less sharp, you have to go in the other direction. So for instance, because whatever you put here has to be an upper bound.
Yes.
So I could do, for instance, I could say this is convergent to order n to the minus 1. Because I could choose a constant times n to the minus 1. I could say this is less than or equal to, say,
Yeah, well,
2 over n.
Yes, yes.
Yeah. So yeah, you have the right idea, just have to go in the other direction.
Yes, but we do not say that the sequence AN has the rate of 1 over n, right? 2 over n.
Well,
I think the rate of convergence is exactly the exact bound. Not too much.
Okay, well, then I talk about different kinds of notation. There's
Yes.
a big O, little o,
Big
theta. Yes.
Yes.
So for purpose of this discussion, I'm only covering big O. So if you want to describe a unique, sharpest possible rate of convergence,
Yes.
I believe that'd be like theta.
Yes, I think it.
Yeah.
Yes, the concept of rate of convergence
Yeah.
is about big theta notation. It should be.
For pretty optimal.
Yes.
Yeah. So here we're just looking for an upper bound. We'd like to get the bound as sharp as possible, although big O notation does not require it.
Okay. Maybe I just don't know enough about convergence. I followed the example perfectly.
Okay.
It made what the example shows made sense to me.
Okay.
But I was thinking that is it possible that there is another way of getting this? There is another way of getting an upper bound, but it is not exactly similar to this one.
Oh,
But
okay.
then he just brought it up.
Right. Yeah. Okay. So yeah, and how you get it depends on the expression involved and what you're able to do algebraically to get an upper bound. And in some cases, you might have more difficulty showing that what you have is the sharpest upper bound. At least here, it's relatively easy to do. In this case, we have a rational function, and it would be possible to conclusively prove that.
What do you mean sharpest? I'm sorry, I'm just confused
okay.
now. This whole discussion's confused.
Okay, so an upper bound can be either sharp or I guess coarse is the other term, or simply not sharp. When an upper bound is not sharp, it means that there could be a very large gap between what you're bounding and the bound. So, like for example, I can say that this expression here, an absolute value, I can say it's also less than or equal to 2 over n, but because it is less than or equal to 2 over n.
Yes.
Right.
Or exactly 1.
Yeah.
You can also say it is big O1.
Yes, I can do that.
Yes.
Yeah, but that is not a sharp upper bound because as n gets larger and larger, then it's going to be a very large gap between this and say 2 over n or 2.
Okay, so when we want it to be sharp, like the closest we can get to the upper bound, or the biggest difference we can get.
Yeah, because a sharp upper bound is more informative as to the actual behavior of the sequence as it goes towards its limit.
So the rate of convergence concerns the systematic rate of convergence.
Yeah. So unfortunately, when rate of convergence is defined in terms of big O notation, it's it can be ambiguous. Because if I make the statement that this sequence is convergent to 2 of big O of n to the minus 1, because I'm using big O notation, that's a correct statement technically, but it's not the most helpful because it's also big O of n to the minus 2. And that better depicts the rate. Because if I look at, say, this sequence versus this one, as n goes to infinity, the ratio between these is 1, goes to 1. So this sequence very accurately depicts the convergence of this one. This is going to 0. Like if I were to plot these, they track each other pretty well. But if there's 2 over n, then you see them like, yeah, this is going to 0, this is going to 0 much faster.
Right. So the actual space.
Yeah.
So we're losing efficiency in that case.
Yeah. Because if we have an algorithm that, an iterative method that converges with a big O of 1 over n, or n's number of iterations, and one that converges big O of 1 over n squared, we definitely prefer this one. That's why it's important to find out what the convergence is. And like we will be learning about methods for finding roots that have different orders of convergence. So that's going to be one of the criteria, or we're selecting them. But there are other criteria too that affect the choice. And actually, you easily, reasonably conclude that the best choice is not necessarily the one that has the most rapid order of convergence.
Okay.
Because of other things.
So, Professor, the point here, I can also say that the right-hand side equals the big O of left-hand side.
Wait. Okay. Wait. Right-hand side of.
Right-hand side of
This?
That is, yes. Right-hand side equals big O of left-hand side.
Oh, it's the other way around.
Yes.
Yeah. This is big O of this.
Yes.
Yeah. Okay.
We
Yeah.
also say that.
It doesn't go both ways because of the direction of inequality.
Okay.
Yeah. Now, if you're thinking of like okay.
But actually, they have the same.
In this case,
Yes.
if I've made this sharp or sufficiently sharp, then yes. So yeah, I can't. Okay, so that's what you're getting at.
Yes.
That in this, how these times work out. Yes, I can say that this is big O of this.
Yes.
Okay, and when you, which is also works as a definition of, I believe, this big theta notation, that it is bidirectional.
Yes.
Yeah. Okay. Sorry, I misunderstood the direction of your comment there. Okay. Other questions before I do more convergence? Right. Chat here. Okay.
I really don't miss real analysis. My brain does not work like this.
Okay.
Ugh.
All right. Now, that example was about convergence of a sequence, an, as n goes to infinity. But we can also look at convergence of a continuous function, f of h, where h is going to 0. And this is going to be important when we look at approximate derivatives or integrals that naturally depend on some kind of spacing between points. And h is a letter that's commonly used to refer to that spacing. So we have a similar definition of big O notation for functions. So the same kind of inequality that fh is big O of g of h. But this time, instead of looking at n going to infinity, we look at h sufficiently small, so because h is going to 0. You can almost think of h as playing the role of like 1 over n. Okay. So then, we have a similar definition of rate of convergence. So if f of h converges to this value f naught as h goes to 0, then this is a rate of convergence if the difference is big O of G of H. So now I'll show you an example of that. So here's our expression, sine H over minus H over H. And if you were to take the limit of this, you would find that it converges to 0. And then over here we're using the limit that as H goes to 0, sine H over H converges to 1. That can be used to figure out that this limit is 0. So what we can do is replace H with a Taylor polynomial. So I've chosen this remainder term. So we have the first two terms of a familiar Maclaurin series, spinning around H equals 0, and then this is remainder. And as a reminder, this is what I have for this is just repeating a statement of Taylor's theorem. So in this case, I'm using n equal 3, and here's my remainder. Remember, the fourth derivative of sine is sine, and that's how this remainder term comes about. So now, I'll go ahead and take this expression for sine h and substitute it in here. Okay, so we have h minus h all over h. So once I substitute this in here and simplify as much as I can, then this is what I get. And we determine that the rate of convergence is h squared, because that is, these terms are dominant. As h is going to 0, h squared is going to be much larger than h cubed. So the rule of thumb you can use, so in a case like this where you have multiple terms to consider, we're dealing with a sequence like the last example, or a function like in this example, whatever power that's closest to 0 gives you the sharpest rate of convergence. So that's why it's this term here. So we're dealing with, in the case of sequences, we're dealing with negative powers of n. And you choose one of those that's like least negative, or closest to 0. Here is the function f of h, as h is going to 0, you have positive powers of h, and you choose again the power that is closest to 0. So questions about how this example turned out to be big O of h squared? Taylor's theorem is very helpful for cases like these, because whatever function you're dealing with, whatever function you're analyzing the convergence of, you can approximate it by a polynomial. Let's see. Okay, this is a perfect time for a quick break.
This is maybe theoretical for now. Okay. Yeah.
Okay. Alright, so here's another example involving convergence as h goes to 0. In this case, regarding a very important topic that we'll see in chapter 9, approximation of derivatives. So here we have most commonly used approximation of the second derivative of a function at x naught. It's called a centered difference. So we use value of f at x naught minus h, and x naught plus h. So we want to see how, as h goes to 0, how rapidly does this approximation converge to f double prime of x naught. And what we can do to figure it out is use Taylor expansion. So you already have Taylor expansions of f of x naught plus h and f of x naught minus h, out here, and we see they're quite similar, there's certain sign differences. And here's the remainder term I've used, and in the remainder term, the derivative is evaluated at an unknown point. So in this case, the unknown point at C1 is between x0 and x0 plus h, and then this unknown point, C2, is different. It's between x0 and x0 minus h. So now, if I take these two Taylor expansions and substitute them into here, we have a lot of cancellation. And what remains, is notice like these terms here, f of x0, f prime of x0 h, and f prime of x0 times minus h, these cancel. And these terms of order h cubed cancel as well. So what's left is this term right here. So what we see is the error is order of h squared, but I actually want to try to simplify this if I can. And for that purpose, I can use the intermediate value theorem. So if we assume that this fourth derivative is continuous, then by the intermediate value theorem, there is some point between C1 and C2 at which the fourth derivative of f is equal to the average of these values. So that is what allows me to replace, I don't want the 112. I can replace this expression by the fourth derivative at a different unknown point that is between x1 and x2, and therefore it's certainly between x0 minus h and x0 plus h. So this is the simplest error term that I have. Well, it's customary to write these approximations using this form. So this is what I want, f double prime of x0. This is what I'm approximating, and that is equal to the approximation itself, and then the error term. So it's minus h squared over 12, fourth derivative at an unknown point. So this approximation, whoops, and I'll write this down, is known as the center difference, is said to be second order accurate. The key to this level of accuracy, by the way, is, this actually came up in one of my other classes today, where I also talked about this same approximation, is the symmetry, that x naught is halfway between these other 2 points, x naught minus h and x naught plus h, which is what leads these two terms to cancel. I can actually use any 3 points to approximate the second derivative, but in general, that approximation would be order h rather than h squared. But because of the symmetry of the points used, we get more accuracy. So as h goes to 0, the error goes to 0 much more rapidly than it otherwise would. Okay. So this is something we'll see more of when we get to section 9.1, where we'll learn about several finite difference formulas like this one, for approximating a first derivative, second derivative, whatever order derivative you like, and how to determine the rate of convergence of these approximations as h goes to 0. Okay. Are there questions about these examples of convergence? Actually, I'm going to do a quick MATLAB demonstration of this convergence. Okay, so I need to stop sharing for a moment. Oh. Share MATLAB. So so do the table following the second derivative, and I'm going to let f of x be equal to something simple, like sine x, and I'll choose x naught equal to, let's say, pi over 4. And I'll choose h equal to 0.1. So I'll fill in those values. All right, so f is a function, and just so I can say f of something, just to simplify the expressions. Okay, so if I, yes? Oh, whoops. Not sure what I was thinking there. Okay. Well, pretend I never did that by deleting it from my command history.
We saw nothing.
Oh, too bad it's in the video forever, but okay. All right. Well, thank you for letting me know. I really need the day to be over. So my approximation will be as shown x naught minus h minus 2 f of x naught plus f of x naught plus h all over h squared. Okay, actually we'll do format long. Okay. And now the exact value, of course, the second derivative of sine is minus sine. Okay. And we see here, well, they somewhat agree. So let's look at the error. Okay. So the error, the relative error, I might add, is okay on the order of 10 to the minus 4. So that's pretty good. So now I'm going to reduce h by a factor of 10 and compute the approximation again. You can already see there's much more agreement between the approximation and the exact. So let's take a look at the error. So notice the error, the significant digits are fairly similar. So the error decreased by a factor of roughly 100. And that's what you'd expect from second order convergence, that I decreased h by a factor of 10, the error decreased by a factor of 10 squared, roughly. So now I think, well, why not just keep going? Let's make h even smaller. And I'll show you what happens as I do that. So like 0, 0, 1. Let's do the approximation, and let's see what happens to the error in this case. And sure enough, it continues. So if I get greedy here, by a factor of 100, so the error should decrease by a factor of 10,000. Let's see if it actually does that. No, it does not. The reason why will become apparent in the next section. So this is a preview of section 2.2 on computer arithmetic. So this approximation has multiple sources of error. The error that we've been discussing here today is discretization error. You're replacing f double prime of x naught by its second approximation because so we have that error is proportional to h squared. But there's also round off error. And so what can happen is that as h goes to 0, these values approach one another. So what ends up happening is, and this is something I'll get into in the next section, that the round off error can be actually unusually large in that case. So that's why you have to be careful using these finite difference approximations, that as h goes to 0, the error will get smaller to a point, and then it'll backfire on you and actually increase. Like here I have h equal 10 to the minus 5. If I did, say, 10 to the minus 8. Yeah, so, yes, so if you were to graph the error as a function of h, you would see that it would decrease,
Yes.
and then it would bounce back up. Yeah, because the round-off error would increase. Because that's being divided by h squared, it's being divided by something smaller, so that part's getting larger. So that's unfortunate. So cautionary tale for you. Okay. I didn't expect to get through everything that quickly. That's why I'm killing time with the MATLAB demonstration. But it also means that we have time for homework questions, and since I technically have 2 assignments due tonight, again, technically, I would imagine that people have hopefully gotten far enough through them to have questions. So, anybody either here or out in Cisco land?
Are we allowed to ask about concept?
Yeah, anything.
Okay, I didn't know. The very, very last problem from the concept.
Oh, yeah, I've got some questions about that one.
Yeah, I was just wondering if that was one where you wanted us to make like a generalization based on, or like like an inference. An inference is the word I'm looking for.
Oh, okay. Okay, let me need to stop sharing here.
Or number 12. I'm asking about the concept quiz on that. Yeah.
Okay. Hold on. Okay, so okay, the role of Taylor expansion plays in determining a rate of convergence. So actually, the example that I showed with sine, there's a similar example in the text with cosine.
Okay.
So when we replace the function involved by Taylor expansion,
Yeah.
what does that give us? Because why is it helpful to change the function? We changed the way in which a function was expressed.
Right.
Yeah. So.
I'm not sure if you're actually wanting me to try and answer that or not.
I guess it's not here. But,
Okay, cool.
Yeah, we try to avoid. I know sometimes I've given away answers in class.
Okay.
And that's really all I want to think about is the various steps that we take in solving these problems. Why do they matter? And this is where any reasonable interpretation thing comes into play.
Yeah. So we are kind of like based off of these examples.
Yes.
A lot of these are just directly stated in the book. So this one is kind of meant to be based off of inference or.
Yes.
Okay. Got it.
Yeah.
Just making sure I'm not missing something.
Yeah, because really to get you to think about the problem-solving process from this case, because a lot of times students are the little sequence of steps, and then they go ahead and execute them, and they may even get an A on the test, but not really understand why they're doing things, what value there is in these steps, because that's what allows you to apply those steps in other problems, to have an understanding of why they're taken.
Yeah. Okay.
There's also a comment that's made at the beginning of the section, or actually, that was the first exploration in this homework, about different types of functions and what you can do with them, and how some types of functions are easier to work with than others. A device like Taylor expansion is a way to work with a function in a different form.
Thank you.
Yep. All right. Well, I might add that although I am pretty loose in what answers I accept, when I read these, my BS detector is on. So keep that in mind. Sometimes I get some doozies.
Dr. Lambers?
Yes.
With regard to submitting the concept check questions,
Yeah.
are you okay with us just uploading a PDF instead of
Yeah,
typing.
lots of people do that. Yeah, like if you include as an attachment here.
Excellent.
Yeah.
Thank you.
One thing that's helpful though, for those of you who do that, I know this will be kind of a pain, but my preference anyway is for a question to be included. That way, I guess if I'm not sure about an answer, if I should accept an answer, I want to get a look at the wording of the question and use that as my judge. Other questions? Rules of time.
Oh, Professor, about the MATLAB demonstration, the example given. Yes, this one. So the reason is that the h square is in the denominator, right? So when h becomes very small enough, and it will enlarge the error of the numerator.
Yes.
Caused by the numerator.
Yes.
So that is the reason, right?
Yes. Yes. So that's because what's happening is the round-off error that's incurred from performing this computation is not really proportional to h. So we have so what's happening here is the error that we get from carrying this out, like for h to 10 to the minus 5 and 10 to the minus 7, is not really going to 0. But because the denominator is going to 0, yeah, then whatever error we get here is amplified even more as h gets smaller.
Now, if that were to continue going on,
Yep.
the error were to even get, or h were to even get smaller, could it bounce back the other way?
Oh,
Right.
it will not.
Okay, it won't.
Yeah.
Okay.
Yeah, so there's, so you get a pretty good idea of what the minimum would be.
Yeah.
Yes.
Mm-hmm.
So how to find the optimized point?
Like,
Can we portray the image of h and the error?
Okay, so let's see. All right, the biggest no fly here, so we'll see how this goes.
So this is the exponent.
It's impressive.
Okay.
We can find the breaking point.
So what I'm doing is I'm storing the errors I get in a vector, a column vector. That's why I have error I, column 1. Okay, so at least that works. So I look at the error, and we see that it's nice and small, and it's larger and larger. But now if I do, okay,
Plot it.
now I want something to plot it against the powers of h. So I do dot exponentiate of, okay, so starting at -1, okay. So those are my, whoops, one column vector. So these are my h values. So if I do a log scale plot of the error against the h values, actually, let me make sure I have no figure windows. Okay.
Oh,
Well, actually, we should read the graph from right to left.
yes. So
Yeah, so it's going down, and right around here, 10 to the minus
4.
4, yes, is where it hits bottom, and notice how it gets steadily worse after that. So this shows that the the error, because here the error is decreasing like order h squared. Here it's increasing like order h to the minus 2. And what this shows is that the error in the numerator that comes from performing those computations of f of x naught minus h, etc., is roughly about the same. Like fairly independent of h. All the growth is coming from a division by h squared. Yeah. On the other hand, if I had a lower order approximation, like we'll learn some approaches for computing the first derivative using where the error is order h. You have the same kind of pattern where it's decreasing and then will increase. But then what happens in that case is the minimum is at a smaller value of h. It takes longer for it to go back. What I should mention though is that, so here we have h to the minus 4, where it bottoms out. So h squared is on the order of 10 to the minus 8, which is square root of, roughly the square root of machine precision. It's generally pretty safe at looking for accuracy of that level, but below that, you may have ground level error to contend with. This was a complete disaster after a while. But again, like if you choose 10 to the minus 4, the error that you have is proportional to 10 to the minus 8. That's pretty good. Okay. Still have some time. Any other questions? Okay. Let's call it night because exhaustion. Okay. I'll stick around in case anyone has questions. Okay.
Thank you, Dr. Landers.
Sounds good.